Hello and welcome. In this lecture, we're going to be talking about LTSPICE. Before we jump into the content, you can see here that something has changed, and that is I'm no longer writing the words and letters by pen. I've decided to use text boxes to be able to make the video format better and save time while recording. So you can see that as the channel evolves, I'll point these things out to you and get your feedback in the comments. So let's talk about the content. So we're going to be talking about an introduction to SPICE, the SPICE engine. We're going to be talking about LTSPICE Basics, and we're going to do our quiz problems introduced in the previous lecture in this lecture and simulate them in LTSPICE. Now, a note here is that I had to cut the lecture 6 into 2 parts because there was a time limit in my recording program. So we'll be finishing the quiz problems in this video and while learning how to use LTSPICE. So let's talk about SPICE and what it stands for. So SPICE stands for Simulation Program with Integrated Circuit Emphasis, and its capabilities are nonlinear DC, nonlinear transient, and linear AC analysis. And we'll be discussing these as we go forward. I'm just giving you a high-level description in this lecture. Now, what components could we simulate in SPICE, the engine? We could simulate resistors, inductors, capacitors, independent voltage and current sources, and a variety of different components that most likely we're not going to get into in this lecture series. Mainly, the components we're going to look at are resistors, inductors, capacitors, voltage sources, maybe switches. We may or may not touch on BJTs and MOSFETs based on how many lectures we have. I don't want to make too many lectures for this series. But certainly at some point we'll have to learn about these components if we want to be good engineers. Now you might be asking yourself, why SPICE? Why is it useful? What do we need to learn about it? So the first point here is that IC design differs from discrete design and prototyping. So a couple of decades ago, when you wanted to design a particular analog circuit and you had resistors, capacitors, inductors, or transistors and diodes as components, you would gather these together, place them on a breadboard, and probe around the various nodes to measure voltages, and use an ammeter, for example, to measure the current through a particular branch of the circuit. These days, though, it's not as simple anymore. You have very sophisticated IC designs on semiconductor materials, and you have to consider heat, power dissipation, consider size issues, capacitances, parasitics, and a variety of other factors. And basically, you can't just invest all that money into, for example, if you have a company, you pay your engineers, you have to pay for millions of dollars for devices. You can't just continue building ICs and just using some very expensive test equipment to continuously measure them and change the design like that. That cost will be prohibitive. So what the industry does is they use powerful tools like SPICE and similar programs to tweak the designs on the computer, try to optimize them, and once a reasonable solution has been generated, they would go ahead and produce a particular lot or a particular sample size of those and go forward with that and try to optimize it better in the physical world by making some adjustments, tuning it, and whatnot. We're not going to get into that here. But the point here is that this program really does help us in terms of driving down cost and time and labor and so on and so forth. The second point is that it is an excellent tool for intuiting electronic circuit behavior. So as we go on and learn more, and this is key for our lecture series pretty much. This point was for your future, and if you get into IC design or circuit design, that's what matters for that purpose. But for our purpose, point number 2 is very important. We want to be able to not only perform circuit analysis on paper, but we want to be able to check our homeworks, for example, check our problem sets, get an idea of how this works, get practice for the real world. That's what we want to do here. And as we discussed while talking about point number 1, this is a de facto industry standard. Either it's SPICE itself or it's some sort of variance of it, variety of it, PSPICE, HSPICE, LTSPICE. So that is another reason why we'd be using SPICE, the engine. Number 4 is that it's available in the public domain. So for example, LTSPICE, which is what we're going to be using, you could find that online, and I've shared that in one or more of the video descriptions on my channel. So let's talk about a typical SPICE anatomy. So a SPICE source file consists of the following structure. There are data statements which describe components and their interconnections. For example, a resistor and how it's connected to one or two nodes. A control statements which describe to SPICE what type of analysis to perform on that particular circuit, and output statements which specify what output shall be printed or plotted. So let's look at a very basic example here. So the netlist is the way that SPICE actually does what it does. So in the old days when SPICE first came out of Berkeley, you'd probably need to write down, so say we have a circuit here, it has a voltage source, two resistors, and a bunch of nodes here. So the first thing is you'd want to specify where the ground node is. This would be node 0 or 0 volts, and you would have so node 0, 1, and 2 here I've labeled. And so how you would start is you would start with the circuit description in the netlist, and you would have the voltage source V1 is going to be here. Then we're going to have the convention is that you're going to go from the positive, the higher node, to the lower node. So node 1 has the higher potential, that's the positive node. Then you're going to have node 0, then you're going to have the value of that component, so in this case 10 volts. And we're not going to put in the unit here, it's going to ignore what's after this number. So then you're going to have resistor R1, and you're going to specify its interconnection. So it's going to be from node 1 to node 2, and it's going to have a value of 10 ohms, as you can see. Then lastly, we have R2, which is connected between nodes 2 and 0, so the higher node first again, and the lower node 0, and you're going to have 10 ohms for that as well. And then we're going to have SPICE directives. So what kind of operation do we want to perform? So in this case, I'm going to have a .op, which is an operating point. You're getting introduced to this idea without seeing transistors, so it might not make sense what an operating point is. But essentially, the operating point is one of the simplest types of analysis. It's a subsection of DC analysis, and it's concerned with finding the voltages and currents through across various nodes and through various components. So for example, if you have 10 volts here and you have 10 ohms and 10 ohms for two resistors in series here, you have what's called a voltage divider, and you're going to have, because these resistors are the same value, you're going to have half of the voltage source be distributed across here. So you're going to have plus minus 5 volts here. So basically, by performing the operating point analysis, you're going to find the voltages everywhere. So you're going to see 10 volts here showing up here, 5 volts showing up here, and 0 volts here. And then you can use that to calculate the currents through various elements. And then we're going to have a dot end to specify that we're ending the circuit simulation, essentially. Now, do keep in mind, though, that SPICE itself, when it came out in Berkeley, they had to use netlists, and that was really the only option initially. But people have developed graphical user interfaces, or GUIs, and the program that we're going to be working with is we're not really going to be concerned with netlists as much. Although I may pop in an example here and there just to remind you that what's going on underneath the hood, basically under the hood. But our primary goal is to learn how to perform circuit analysis and to check our designs or our circuits that we're going to be analyzing. So really what we care about in this lecture series is to first familiarize ourselves with these simulation softwares, and also just check our solutions. So LTSPICE is one variant of the SPICE engine, and it adds a graphical user interface to SPICE, making it easier to visualize circuits. And that's what we're going to be using. And let's real quick talk about DC analysis. There's other types of analysis such as transient, AC, etc. But we're going to only be talking about DC analysis for a while, since we want to get familiarized with that, and that's what suffices for now. So DC analysis determines the DC operating point of circuit. So this might not make sense right now, but it treats inductors as short circuits and capacitors as open. We're going to discuss that later when we get to that chapter. It can be invoked via the .dc, .op, and .tf commands. Again, that's something that I'm only introducing right now. We're going to talk about later. And it's going to be performed before other forms of analysis. For example, transient or AC small signal. So when you click on AC small signal or transient analysis, it's going to have to do the operating point analysis first before you can move on to performing your desired analysis. Okay, so let's go ahead and talk about LTSPICE Basics. But before we do that, let's go ahead and discuss a problem that we're going to use as an example, as a case study to learn about LTSPICE. I personally like to learn through examples, so before we do that, let's first set up the problem. This is the same problem that I showed you in the netlist example, but since we haven't talked about voltage dividers in a formal way yet, I'll just go ahead and derive it really quickly. So let's just go ahead and, so the question is asking us to find Vout, output voltage in the circuit below, and check the answer using LTSPICE. So let's do part 1, which is to find Vout, an expression for Vout in terms of V1 and R1 and R2. Let's just go ahead and assign various signs here. So I'm going to say that V1 is applied here, so there's going to be a voltage drop from this side to this side of R1, and also for R2 it's going to be from this side top to bottom here. That's the voltage drops across these resistors, which should sum up to V1. Let's go ahead and do a KVL here and call this I. So that's the current flowing from the source going through this loop. And using KVL, then we can find that negative V1, I'll just go ahead and not use colors, so negative V1 plus, it's going for, the current's looping through plus to minus, so that's a positive according to passive sign convention. That's going to be a positive sign I times R1. Again, it's going to go clockwise and see the positive sign first, so I R2 is going to be my next term. And then I'm going to set that to 0 because it's KVL. Sum of all the voltage rises and drops should equal to 0. Now let's go ahead and solve this in terms of I. So I'm going to move V1 to the other side. I'm going to factor I out simultaneously. So I'm going to have I, then I'm going to factor that out and get R1 plus R2. And I'm going to solve in terms of I. So I'm going to divide both sides by R1 plus R2. And I'm going to get V1 is I is equal to V1 over R1 plus R2. Now keep in mind, this is just the current through this entire circuit, but I want to find Vout, which is the voltage. And recall that if I probe here from plus to minus, the voltage Vout here is the current through R2 times the resistance R2. So I'm going to get that Vout is equal to V1 over R1 plus R2 times R2. So V1 R2 over R1 plus R2. And that's what I mean by the voltage divider. It's a very common circuit you should know. Although we're going to talk about it in the next couple of lectures, it's good to just get a preview now, since you're going to see this a lot in your future endeavors and in homeworks and exams. It's a very fundamental concept. So now, with the parameters that we saw before, let's just go ahead and plug those in. The voltage V1 was 10 volts. R1 and R2 were the same, and there were 10 ohms, just to make things simple. Make the only concept to be learned the actual circuits in LTSPICE and not the math. So let's just say that's 10 ohms. Now what I'm going to get then is 10 volts times the ratio 10 over 10 plus 10, which is 1/2. So 10 over 20 is 1/2. That's 1/2, and that's equal to 5 volts. So the output voltage is 5 volts. And the general rule of thumb is that for a given circuit, for a given voltage divider, and sorry, it's not a rule of thumb, it's just a truism, it's a fact that if the resistors are the same value, the output voltage is half the input voltage, as you can imagine. Whatever R2 and R1 is, if I say R is equal to R1 equals R2, let's just make a new variable. Then if I plug in Vout equals V1 R over R plus R2, that's just 2R. And you're going to always get that as V1 over 2. So as long as these are the same value, you're going to have the same a voltage drop of half a voltage drop for the input across the output. So with that being said, let's jump to LTSPICE then and begin looking around here. Let's see, I gotta fit the screen onto here. Okay, so what you see here is a typical program. So you have a file, a menu, a drop-down menu. You have edit. You can do various things here. Hierarchy. We're not going to worry about symbols yet. We're not going to create any symbols anytime soon. For this lecture series, you're going to see SPICE netlist and SPICE error log and visible traces. We're going to look at these at some point. Simulate. You're going to click on run. Usually when we're going to do our simulations. We're not going to worry about efficiency yet. Tools, export netlist is something we may use. Window, we can adjust the windows here, and help, you can look at the LTSPICE help logs and all those things. But to simplify things, 1 second here, I gotta fix this problem. Okay, so let's just go ahead and create the circuit, and the way I'm going to do that is I'm going to go into the components section and look up voltage. Look up voltage and then click on voltage here, place it, click, and press escape. Then I'm going to put down 2 resistors from this menu, from this option. I'm going to press Control R to rotate and place it in a nice manner. Then I'm going to click again, first Control R and click again. In this location, I'm going to press escape, go on here and click wire. That's going to allow me to draw wires. I'm going to connect these nodes, and once you click from one terminal to the other, it's going to terminate the wire. So you create a new one from this terminal to here, then another one from here to here, and there. Now let's go ahead and do something here. Let's go ahead and label the nodes. Let me just teach you this from the get-go, because it's going to simplify things when we have a larger circuit. It's good to label things, label nodes. So let's just press escape, go on this option here, label net. Then I'm going to write down node 1, say OK, and press this node as we showed in the netlist example. I'm going to also click here and call that node, let me press escape and right click on here, call that node 2, or it could also be vout, that's fine. Then I'm going to label this other node down here as net 0. On here, let's go here, net 0, and that's going to automatically call that ground. So I'm going to put that there, click on wire, and connect that node. So now that's a very important note there, is that you have to always have a ground reference point when you're trying to simulate circuits in SPICE, and specifically LTSPICE. So let's now go ahead and give some values to these components. So right click on them and say DC value of 10 volts. Right click on here, say 10 ohms. And it's going to automatically be in 10 ohms. We're not going to worry about all these other things yet. It's just very simple. We're going to begin very simply. Put 10 ohms. Then I'm going to go to, let's go ahead and look at the netlist before we do anything else. So in the netlist you can see, as I showed you an example about netlists, we have the source V1 and positive connected node 1 and 0, then the value 10. Then for R1 we have the next node 2, then the first one 1 and the value 10 ohms. Then for R2 you have the other node is 0, then the other connection is 2 here, the value is 10. Then you have a dot op. These are so that's the circuit description, and these 3 are the directives. And dot op and dot end are what we saw before, but the dot back anno is an option for annotation, for being able to look at the current going into a pin, which at this moment we're not going to worry about. So now that we saw the example of a netlist, we're going to go ahead and go into either simulate run, or just click on run here. And I'd already placed a directive here. Let me go ahead and see if I can find it here. It's not placed down here, but I already placed a directive of .op, and it's showing me the results here, which I see that the voltage at this node with respect to ground is 10 volts. The voltage at node 2 with respect to ground is 5 volts, which is what is expected. It is half of the source, given that these are equivalent resistors. And the current going through R2 is negative 0.5 amps or 500 milliamps, and the direction is because although on paper the current's going to flow this way, the way that netlets are generated, they always go to the positive terminal or the last terminal, and then they're going to list the first one. So we saw for R1, for example, it was R1 2 1 10. So it's looking at the other terminal. So when it's calculating the current through, it's going to be the opposite direction of the clockwise current flowing through here, which we know should be the case because we have a high potential here and lower potential here, and these are just passive elements, so it should be a standard current flowing clockwise. So that is the reason that we're seeing a negative number here. It is just the fact that the netlist is generated in the manner that it is, listing the other node first and then the first node you're originating from. Okay, so for the quiz, we begin with a classic problem that you're bound to encounter at some point during your circuit analysis course. So in this problem, we're asked to find this unknown voltage Vx in the middle of the circuit here. My only hint here would be just to make sure you stick with the rules that we've learned and just follow through from there without panicking. Problem 2, we have a question asks us find V1, V2, and V3 in the circuit below. My hint here would be to again follow the rules that we've learned and try to first simplify the circuit as much as you can in terms of architecture and the way it's represented before you begin solving it. Now in problem 3, we're asked to find again an unknown voltage Vx in the circuit when the current is defined as shown here. Okay, so I'll let you give it a try and box the final answer as best as you can, and I will begin with problem 1. So we're going to find the voltage Vx. So I'm seeing one big loop in the circuit, so I'm going to use KVL, and I'm going to use, since I don't have space to draw it here, I'm going to do it from the outside. So my direction is in this way, and I'm going to call it I, lowercase I, and write KVL equation 1. So I'm again going to start from the very bottom here, as I usually do from the source, and I'm going to say go clockwise and see what I encounter. So now before we do that, note that because I've called the current, I've defined it to be clockwise, I'm going to label things as if it really is clockwise. So I'm going to say for it to be clockwise, then the voltage drop across the 10 ohm resistor is going to be in this manner, plus and minus in this fashion to follow passive sign convention. And similarly for the 30 ohm resistor, I'm going to have the same sign. And that's I'm making an assumption. I'm assuming that the current is flowing in this counter or clockwise direction. And we'll see if I'm correct, if I get a minus or a plus. So I'm going to write my KVL. So I'm going to start from the down here and say, okay, go up and see minus 50. And I'm not going to color that red. I'm just going to quickly go through minus 50. I'm going to keep going. I'm going to see a voltage drop here that should be, by Ohm's law, 10 times the current. So plus 10 ohms times I. I'm going to keep going, and I'm going to see, and don't confuse this plus, that's a whole different story. Look at this guy. I'm going to see a plus. That's going to be a plus 30 ohms times I. I'm going to keep going. I'm going to see a plus 30 volts, plus 30 volts, all that equal to 0. So let's go ahead and solve this guy. So I'm going to cancel the 30 and minus 50 and get a negative 20. But I'm going to move it to the other side of the equation. Then I'm going to have 20 volts is equal to 10 ohm times I plus 30 ohm times I. So that's 40 ohms times I. And I'm going to divide by 40, and I'm going to get I is equal to 1/2 or 500 milliamps. 1/2 amps or 500 milliamps. And I'm going to circle that even though it's not the final answer. Then I'm going to look at my circuit and look at Vx. Vx is when I use the probe to measure, put the plus here, put the minus here, the minus end, and measure here. I'm going to see that it's going to be from the bottom here. It's going to be, I'm going to be going up, and I'm going to think, okay, from ground of my probe, from the ground of my probe, I'm going to go up and get a 30 volt voltage rise. But then And again, I'm going to keep going, and I'm going to see a whatever this voltage is here, a rise here, because I'm going minus plus minus plus. So I'm rising twice with different amounts. And do note that I have a positive current, so my assumption was correct. And the voltage drops are indeed in the manner that I've shown, and the current direction is clockwise. So given that, I'm going to go ahead and say Vx is equal to, I'm going to start here, go up 30 volts, and then go up another 30 ohms times I, which is let's say 0.5 amps. That's going to be 30 times 0.5, which is 15. So 15 volts equals 45 volts. So Vx is equal to 45 volts. And let me circle this guy, or box this guy. And now we have to make sure that we check on the other side and make sure that there's no conflict here. So I'm going to look this way and say, okay, let me start at the ground, start at the bottom, at the reference node, go up, and I'm going to see a rise of 50 volts, and keep going. I'm going to see a drop because I'm going first from minus plus, then plus to minus. So I'm going to see a drop here. Therefore, I'm going to have a Vx is equal to going up 50 volts, dropping by 10 times I. So I'm going to have 50 volts plus or minus, because I'm going to drop whatever that voltage is. So plus to minus is going to be a drop, so that's going to be a 10 ohm times 0.5 amps, so 0.5. That's going to give me 10 times 0.5 is 5, so 50 volts minus 5 volts is 45 volts. And we are indeed getting the correct answer, which is shown here, so that's correct. So really quickly here, just to verify, we could have also said with KCL, I used KCL, I could have said, okay, let's use Ohm's law from this node, this point to this point. So I'm going to say the current again, I'm going to assume it's going clockwise, and say 50 volts minus Vx over 10 ohms. This current, then that's the current. So this voltage minus this voltage over the resistance, that's the, using Ohm's law, that's going to give me the current I. That's equal to I, which is equal to Vx minus 30 volts. Vx minus 30 volts over 30 ohms. I'm going to go ahead and cancel the 10 from here and here and get a 3 on this side. And I'm going to multiply 3 on both sides and get 150 volts minus 3Vx is equal to Vx minus 30 volts. Then I'm going to add it to the other side and get 180, and add 3Vx to the other side and get 4Vx. And once I do the division here, I'm going to get 180 divided by 4 should be actually, we should know that answer from trigonometry because of angles. That should be 45 volts. So okay, so for the first quiz problem, I've gone ahead and drawn the circuit out just to save us time. There's no more new skills that I haven't shown you in the first example. I think the only things to keep in mind are what these figures do here. If you need to move anything, you can use these hands here. And these are really just things you can figure out on your own by fiddling around with the program. So I'm not going to spend any more time on those things. So you've already seen the naming. I've named this node Vx as in the problem. Now I'm just going to go ahead and show you this since the first one didn't allow me to. I'm going to click on Simulate Run, and I'm going to go to DC operating point at the end here and click OK. And that's going to calculate the values for me. So let me just move this here. And we're going to see here that VN1, I haven't labeled this node, but it's node 1 here. It is 50 volts as expected with respect to ground. Node Vx, which is what we care about, is 45 as we calculated. Node 2 here is 30 volts as expected with respect to ground. And the current is again negative because of the reason I told you earlier, the way it's defined in the net list. It goes from the second node to the first node. So therefore we have a negative current, but the magnitude is 500 milliamps as calculated. And with that being said, then this confirms our calculations for the first quiz problem. So in this problem, we're asked to find the voltages of V1 through V3. Before we do anything though, let's try to simplify things. So I know here that I could draw the equivalent circuit in a more nice fashion and move this node over and make it a more rectangular looking circuit. So I've done, to save time, I've already done this in the circuit below. You can verify yourself by pausing the video that these are actually the same circuits. But I'm going to go ahead and label my currents. I'm going to call this 1, 2, for every loop. I'm going to go ahead and do its own equation. So KVL now. For 1, I'm going to start at the bottom again and go up and see minus 10. That's a minus 10 plus. I'm going to keep going and I'm going to see a plus V3. I'm going to go down again clockwise and see a minus V2. All of that is equal to 0. Equation 2, I'm going to start down here and see a plus V2 as I go clockwise. That's a V2, and I'm going to keep going and I'm going to see a plus V1. I'm going to keep going and I'm going to see a plus 15. All of that is equal to 0. Then I'm going to go to loop 3 and start again at the bottom and go up and see a minus V1 plus, because I keep going clockwise and I see a plus sign and I see a 20 volts. That gives me that. And just for practice, I'm going to have a fourth loop here. Keep in mind that we have 3 unknowns, so really 3 equations would be enough, but I'm going to just for practice show us what's going to go on here. So I'm going to start at the bottom here and see a negative 10 again. Go up and see a plus V3. I'm going to keep going, keep going, keep going. I'm going to see this. This is a larger loop, so I'm going to see a plus 20. Plus 20. Keep going down here, and I'm going to see a plus 15. All of that is equal to 0. So now let's go ahead and solve from the first equation. So the first equation, what is that going to tell us? All that's doing is saying V3 minus V2 is equal to 10. The second equation is telling us that V2 plus V1 is equal to minus 15. The third one is telling us a useful result, which is that V1, if I take it through the other side, is going to give me that V1 is equal to 20. And the fourth one, although we don't really need it, it's going to tell us that if I take 10 from this guy, I'm going to get a 10. From 20, I'm going to get a 10 if I take 10 away. And I'm going to get that V3. Let's see here. V3 is equal to, let's see, V3 is equal to minus, sorry, I was distracted by something else. So it's going to be a minus 25 volts. Now we found V3, so let me circle that or box that. Then I have the relationship up here, which I already found that, so let me box that too, V1. And also that, let's see, we have V1, and we could find it using this equation what V2 is. V2 is going to be minus 15 minus V1, which is 20 volts. So V2 is going to be negative 35. So V2 is negative 35 volts. And we do have another equation up here. Box that and then go up here. We do have this equation up here which relates V2 and V3. Let's double check. So V3 is 10 plus V2, which is 10 plus V2 was negative 35. That gives me a negative 25, and V3 was indeed negative 25. So we're good there. Okay, in this problem, I've also gone ahead and drawn the circuit out to save time. So let's go ahead and simulate this, but before that, let me just indicate that I have chosen the ground reference node to be this node, but it could really be any node, and you just have to be cognizant of where the direction of the V drops, the voltage drops across each component, and you'll just have to shift things around, shift the voltage values around. And really that's the only downside to this, but we do have to make sure it's not ambiguous and we have to put a ground node somewhere. But let's go ahead and simulate this and compare our results. So for R1 here, we found that the voltage drop from the top side to the bottom side, so plus to minus, is 20 volts. So now let's verify. That's node 2, and this is the node. This node is 15 volts because ground is here, so I didn't label it with a name. So it's going to be whatever this voltage is here minus 15 volts. So let's look at node 2. That's 35 minus 15. That's 20, and that is indeed 20 as we found in the problem set by calculation. Now let's go ahead and look at R2's voltage drop. So that is going to be Vx minus 0, which is ground. But the way we defined it is that the plus sign is here in the bottom and the minus sign is up here. So we'll actually have to do ground or 0 minus Vx because it's from the higher potential to the lower potential. And that's going to give us negative 35 volts. Let's verify that ground minus Vx is negative 35. So ground is 0 minus Vx, which is, let's see, I think something... Oh, I think I double named it, so it really should have just been Vx, but I called it V2. So now Vx is replaced by V2. That is 35, so 0 minus 35 is negative 35, as indeed is the case based on our calculations. And lastly, let's look at R3. The voltage drop there is defined as plus being on the left and minus being on the right. That's the convention we follow. So it's going to be a node 1 minus node 2, and that should give us negative 25 volts. Let's look at node 1, 10. Minus node 2, which is 10 minus 35, which gives us negative 25, and indeed that is the answer. So find Vx in the circuit below. Again, we're going to do the same thing as the first problem, and I'm going to write a KVL for this node, and actually it's red, but that's fine. Let me go over this and call this I, because I is shown here on the side with that direction. So I'm going to start at the bottom and say KVL, first equation, I'm going to say minus 40. I'm going to keep going up, and since I imposed that direction of current, I'm going to also label these polarities here to follow passive sign convention. I'm going to say plus 5 times I, plus 5I. I want to keep going, I'm going to say negative 6. Keep going, I'm going to see clockwise, see a plus 10i. Keep going clockwise, and I'm going to say plus 16. And set all that equal to 0, and simplify it. I'm going to have a negative 46 here, plus a 16, which is, let's see, negative 30. Then I have a 5i and a 10i, so that's 15i, equal to 0. That's a negative 30 plus 15i equal to 0, which means that 30 is equal to 15i, and I is equal to 2 amps. That's the first result. Let me write that more neatly. I is equal to 2 amps, as we said. That's not the final answer, but we're going to box that, and that tells us that the current's going in the clockwise direction as we predicted. And what we're going to do next is find Vx. So looking at the right side, if you look at this side, we're going to see that we're going to have to start at the bottom at the reference node and go up and get a rise of 16 volts, and then get a rise of whatever this voltage is, which is 10 times I. So Vx would then be 16 volts plus 10 times I, and I is 2. So I'm going to get 20 plus 16, which is 36 volts. Now on the other side, I'm going to say, so let's call this 1, let's call this 2. Side 1 told us that. Let's see what side 2 tells us. I'm going to start at the bottom, go up, and I'm going to get a rise of 40 volts. I'm going to drop whatever this voltage is, 5i, because I'm going from plus to minus. So initially I went from minus to plus, so I rose. Then I'm going to have a drop here from plus to minus, then I'm going to have a rise again because I'm going from minus to plus of 6 volts. So I'm going to say that Vx is equal to, let's see, 40 volt rise plus a 5i, and I is 2, so that's 10 volts. Well, that should be a minus, I'm sorry. That should be a minus I have a drop here of -10, and I'm going to get a rise of 6. So that gives me 30 plus 6 is 36. Okay, so let's go ahead and look at our final circuit problem and simulate it. So I'm going to go and click on Run, and let's look at what Vx is with respect to ground. And Vx is 36 volts as expected, and the current through all these different components and resistors are 2 amps, and therefore we were correct in our calculations. I hope that this video has served you well in terms of acquainting you with LTSPICE, and I hope you'll be able to do more problems by yourself and learn more about LTSPICE. I'll see you guys in the next video.